Hello and welcome to Maths with Martin. This is the first of a series of videos I'm going to do leading up to the A-level exams, where I'm just going to focus on a different topic in each video. With all of these questions, you can find them if you look below in the description. You can find the PDF of the problem, so I'd recommend that you have a go at the problems first, then come back, watch this, where I go through the solutions. So the focus of this week's one is going to be on logarithms and exponentials. We're going to gradually up the difficulty as we go along. And what I've tried to do is look at problems that are similar to the ones that come up constantly in the A-level exams. Every paper will be different, so it's really important that you practice a variety. But hopefully this video will cover some of the key themes you will see throughout. Now for our first question then, we are going to use the laws of logarithms to solve the following equation. Now in this equation I already have all of the logarithms on the left hand side and all of the non-logarithm terms are on the right hand side, so that's good. On the left hand side, what I want to do is use the laws of logarithms to combine these two terms into one single logarithm. And we'll see why we want to do this in a second. Now, before I use the law that states log A minus log B equals log A over B, I need to deal with the 3 that's in front of the first term here. I can use the power law to bring this up as so. And now, the numbers in front of these logarithms are just 1. Okay, so I need to deal with that part first. So once I've done that, I can now use that law that I mentioned a second ago. Log A minus log B equals log A over B. So this just becomes the following here. So I've successfully got a single log term on the left hand side and I've got a non-log term on the other. Now what I can do is go from this logarithmic form into this exponential form. So I can do 5 to the power of 2, which will equal what's in that big bracket there. So this becomes 5 squared, which is 25, and that's going to equal what's in that bracket. So this will be x plus 2 to the power of 3 over x squared minus 4, and that equals 5 to the power of 2, which is going to be 25. So I'm now going to go ahead and solve that equation for x. But what actually I'm going to do before I just start multiplying through is I can look at the x squared minus 4, and what I can do there is realise that I can use the difference of two squares to write that as x plus 2 times x minus 2. And this will just make my life a little bit easier, because this will mean that actually I can cancel a pair of those x plus 2's to get the following here. This means that I'm only going to have to solve a quadratic equation rather than a cubic equation instead. So now I'm going to multiply both sides by that x plus 2. Sorry, that x minus 2. And I'll arrive at this step. And then what I can do at this point is now I can start expanding everything out. So getting all the terms on the left-hand side here, so taking away that 25x and adding that 50 to both sides, I'm going to get the following here. Now it does say here solutions relying on calculator technology are not acceptable. So we need to show our factorising or quadratic formula or completing the square. Basically just showing a method of how I'm solving this. Even if you do put this on your calculator and then you kind of just write down the factorised form, that's okay. The examiner will never know. but do just make sure that you are showing that method in some capacity. So then solving this, so basically setting both brackets to 0, we get x equals 18 or x equals 3. Just be really cautious that you check these solutions actually work. So substitute back in the x as 3 and x equals 18 into those brackets, and make sure that you are taking the logarithm, working out the logarithm of a positive number here, because you cannot work out logarithm of a number that is not positive. Now we're okay in this case because when we substitute in 18 and 3 back in there, both of those brackets will be positive, but just make sure that that is the case. If you end up having a negative in one of those brackets, then that solution will not be valid. Right, problem 2 is quite a common problem where they say that, a and b equals some type of log, and then you're given some log term that you then need to manipulate into making the terms look a little bit like what you've been given for a and b here. So let's get into it. We've got log to base 3 of 25x minus 100. What I'm going to do is I'm going to first start off by factorising the 25. As so. And then what we can realise is that the x minus 4 is related to what I've been given for b. And we'll actually see how 25 is also related to this. What I'm going to do is I'm going to separate this out using my laws of logarithms, but this time I'm going to use it, go from one term into two terms here. So kind of the opposite of what we were doing in the previous problem. So I'm using the law that log AB is log A plus log B. So I've separated it out like this. And what we can notice is that log to base 3 of x minus 4, we can just call that B. And this log to base 3 of 25, you might be thinking, well, I could put it in my calculator or get some kind of horrible decimal. What we can realise, though, is that A is log to base 3 of 5. And I can write 25 as 5 squared. So try and think about how I can get that 5 involved in this somehow. So I'm going to rewrite log to base 3 of 25 as log to base 3 of 5 squared. Log to base 3 of x minus 4, well, as we said, we can just now call that b. And then log to base 3 of 5 squared. Now, why I wanted to write it like this is I can use that power law to bring that 2 to the front. Again, we're basically kind of doing the opposite of what we do in the first question. So bring that 2 to the front, and log to base 3 of 5, well, I can call that a. So this is just going to be, let's put my equal signs in there. That's just going to be 2a plus b for the first one. So let's look at part 2 of this. So we've got log to base 3 of x squared minus 16 over 45 x plus 4. Yeah, again, do check out the PDF if you want to see a bigger copy of this. It's hard to kind of fit everything on the screen here. So with this one, we're going to start by just playing around with what's in the bracket here. And yet again, I'm going to just do a bit of factorising. So I'm going to start off by factorising x squared minus 16. Yet again, using, my friend, the difference of two squares. It's a tool that can be very useful in a lot of problems. So writing x squared minus 16 as x plus 4 times x minus 4. And we realise that those x plus 4s are going to cancel. So we end up here with x minus 4 over 45 here. And then I'm going to use the fact that log a over b can be written as log a minus log b. To obtain the following. Yet again, we realise that log to base 3 of x minus 4, well, that is just b here. So that will be simple enough to replace. But log to base 3 of 45, at the moment, that's not got a 5 there. So what we could do is look at that 45 and think about how I can bring 5 into this somehow, and realise that, well, I can just rewrite 45 as 5 times 9. So when we do that, just going to write it there as 9 times 5. So what I can do is I can then, again, use the laws of logarithms to write this out. So if I've got log AB, that's going to be log A plus log B. So I'm going to do this. And then we get that log to base 3 of 5. And I've got log to base 3 of 9. Now, I've not been told that that equals A, B, C, or whatever here. But log to base 3 of 9, I can work out its exact value. That's not going to give me some horrible decimal. Log to base 3 of 9 is simply going to be 2. You can check it on your calculator, but the reason why that works is that because 3 to the power of 2 gives you 9. So we can now just call the log to base 3 of x minus 4. That is just going to be b. Log to base 3 of 9, that is just going to be 2. And log to base 3 of 5, that's just a. So this is going to be b minus 2 minus a. By the way, just be really careful that you are taking away both of these, as the instruction is to take away log to base 3 of 45. So when you separate that out, you need to take away both the log to base 3 of 9 and the log to base 3 of 5. So you should end up here with b minus 2 minus a, or some other way of writing that. Let's look at part B. So we're given that f of x is log to base 3 of 25x squared minus 100x, and we're asked to state the domain of f of x. Now, for something to be classed as a function, it must be either one-to-one or many-to-one. And the important bit for this question is that it has to be defined for all values in its domain. So that means that you can put the value of x in and it not give you something that is an error. Okay. Now, we discussed earlier that in order for a logarithm to give you a valid answer, you need to make sure that you're doing log of a positive number. So if you do log of 0 or log of a negative number, you'll get an error. Okay, if you do log of a negative number or 0 in your calculator, you'll get an error there. So in order for this to be defined as a function, we need to ensure that what's in the bracket there, that 25x squared minus 100x, that has to be positive. So basically what we've got here is we're solving a quadratic inequality. Okay, once we've used that knowledge of logarithms, this really is just solve a quadratic inequality problem. So what I will do is I'm going to find my critical values. Okay, these are going to be the numbers that are involved in my final answer. So I'm going to just look at, if I were to just set this to 0 and solve it, so I'd factor out a 25x as so. So my critical values would be x equals 0 and x equals 4. So that means my answer is going to involve them in some way. Really important here, by the way, that you don't just divide through by the x, otherwise you're going to lose that solution of 0. So I can draw myself a little sketch here in order to help me see where all my answers are going to lie. And I'm looking at this quadratic being positive. So I'm looking at where it is, the values of x, which are going to give me values of 25x squared minus 100x, that are going to be above the x-axis. So that's going to be all these values here. So basically, if x is less than 0 or x is greater than 4, then this will be valid as a function. So this would be my domain, that x would have to be less than 0, x is 4. We can just go a bit further here and say that x can be any real number such that x is less than 0 or x is greater than 4. Potentially is also a question could ask you to put that in set notation as well. In this next one, we're going to look at some exponential modelling. I know this is, the modelling in general is something that students find challenging, so I want to try and put quite a few of these modelling style questions in these videos. So in this model, we've got a microwavable meal. It's taken out of the microwave. The temperature of the meal is, after being taken out of the microwave, is modelled by the following equation. You're told that A and B are constants, and you're told that initially the temperature of the meal when it was taken out of the microwave was 80 degrees. Okay, apologies for the way if that's not quite right in terms of the science, but hopefully, the mathematical context is still going to be helpful here. So the first thing we have to do is to state the value of A. So what we can do is we're told that initially the temperature of the meal was 80 degrees. What I always like to do with these questions is think about, okay, we've got all these words, how can we put them into values and equations just to make it something that was really simple. Now, if we're talking about initially, we're talking about when the time, and the time is this little t here, we're talking about when the time is 0, so when t is 0. And we're told that when t is 0, the temperature is 80 degrees, so theta is 80. And I just always find it helpful to just extract the words and just put it into something that's quite nice and simple. Okay, if you just got told, oh, sub in 0 and t is 0, theta is 80 to find what A is, you go, oh, okay, that's fairly straightforward. So let's go ahead and do that. We know that theta is going to be 80. T0, now remember, e to the power of 0, or anything to the power of 0 for that matter, is going to be 1. So that e to the power minus bt part is just going to go to 1, and 1 times anything, it's just going to be itself there. So just going to be that A. And then we've got the plus 20. So A is going to be 60 degrees Celsius. Please make sure that you put your units there because they can mark you down for that. So make sure you've got your units here. Right, on to part B then. We're given that after 20 minutes, after being taken out of the microwave, the meal had cooled down by 27 degrees. Find the value of B to 3 significant figures. So the temperature has cooled down by 27 degrees. So be really careful how you interpret this. What this means now is that theta has gone down to 53 degrees. Okay, not that it's gone down to 27, it's cooled down by 27. So the temperature has decreased by 27. So just take care that you read that carefully. And this is after 20 minutes, so T is going to be 20. Again, I find it really helpful to kind of write all of these things out. So we're going to plug that into our equation. We know that theta is 53. We know that A now is 60. And T is going to be 20. And I've still got that plus 20 there. Then what I'm going to do is I'm going to take 20 from both sides. And I'm going to divide both sides by 60. Before we start introducing natural logarithms, as we'll see in a second, we want to make sure we do what I call isolate the e term first, okay? So what that means is there's nothing being added or taken away after that term. There's nothing that you're multiplying the term, so nothing in front of the e. So we've got rid of that minus 20, we've got rid of that 60, and now we're just left with the following, okay? Basically, you want e to the power of something equals some number before you start introducing logarithms. Usually you'll get your first mark for getting up to that point. Now what I can do is introduce natural logarithms, as we mentioned. So when I take natural logarithms, I need to do this to both sides. So I'd have natural log of 33 over 60. And when I take the natural log of e to the power of a number, it just becomes that number, okay? Because natural log of e to the power of x is just x. You can check that through the power law, bring the x down, natural log of e is just 1. So if we do natural log of e to the power of minus 20b, that's just going to be minus 20b. and then you divide both sides by minus 20. And then this is what we get. This is what it would be exactly, but I'm asked for 3 significant figures. So we just pop that in our calculator and we get 0.0299. Right, now we're on to part C. Firstly, I've just put the key parts that we've found so far at the top there. So part C is find the instantaneous rate at which the meal was cooling after 1 hour of being out of the microwave. Give you an answer to 3 significant figures. I really want to emphasize that word rate there. We're not finding the temperature after 1 hour, we're finding the rate at which it's cooling. So I have a little saying that where we see the word rate, think differentiate, and that's what we're going to need to do here. Okay, we basically want to find out how much of its temperature it's losing per minute at that instance. Okay, it's going to be different values for different times, but we want to find out at the instant of 1 hour after being taken out. So what we need to do is we need to find d theta by dt. So we're going to differentiate theta with respect to t. So above there, I've got the equation for theta. What I've done is just left b, just written it as b rather than actually write it out as its exact value or the rounded value that we found, just to kind of have a bit more accuracy. So remember, when we differentiate exponential functions such as this one, what we're going to do is we're going to multiply by the coefficient of t. So we're just going to multiply this by minus b. So this will become minus 60b e to the power of minus bt. Okay, leave that e to the power of minus bt alone. It's not a case where we take one from the power thing. We're just going to multiply by the coefficient of t. When you differentiate 20, that just goes to 0. So this is our derivative, okay, where that b is that minus 1 over 20 natural log of 33 over 60 that we found earlier. Now we want the rate after 1 hour, and plays a little bit of a trick on you here because our time is defined as in minutes. So what we're asked to do here is find what d theta by dt is when t equals 60. So we're going to substitute in 60 into our equation here. Remember, b is just that constant there, that minus 1 over 20 natural log of 33 over 60. And we can just put this into your calculator. I'd recommend that you use the exact value that your calculator would have found earlier. So you should still have that in on your calculator. Obviously for part B, you had to leave it to 3 significant figures. But my recommendation would be use the exact value just to ensure that accuracy there. Okay, it should already be in your calculator. You can just use the answer function to do that. So when I substitute that in, I get minus 0.298. However, the question asked me to find the rate it was cooling at. So the cooling part of that wording implies the negative. Okay, for example, you wouldn't say I lost minus £20. You would just say I made a loss of £20. Even if you did your calculation, you got minus 20. The fact that you say the word loss implies that negative. So the fact that we say the word cooling implies that negative. So the rate it's cooling, we would say it's cooling at a rate of 0.298 degrees Celsius per minute. Finally, there's a little part D with this question for 1 mark at the end, just kind of testing your knowledge of the model. So I've just put there the original equation there with the A and the B. To be fair, as you'll see in a second, it's not really going to matter even if we've got the incorrect values of A and B. But the meal is accidentally left out overnight. Oh no. By relating your answer to the model, suggest a sensible temperature for the meal the next morning. give a reason for your answer. So if we leave this out overnight, that's going to be 8, 10, 12 hours or so. What that's going to mean is that t is going to be a large number. Okay, so what we're looking at here is what happens as t gets very big. So we can see that what we're going to sort of test there is as t gets large, let's say as t tends to infinity. Now, I know overnight it's not going to be tending towards infinity. I mean, technically here you could just try a number like 600, or which would represent 10 hours. But let's just look at the behavior of the model as t tends to infinity. As t tends to infinity, that e to the minus bt part, that's just going to go to 0, because you're doing e to the power of minus a really, 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 really big number. And because of the negative there, you're doing 1 over e to the power of a really, really big number. If you do 1 over a really, really big number, it's going to tend towards 0. So as t tends to infinity, that first term just tends to 0, and that just means that theta is going to tend towards 20. So we're going to say there that 20 degrees Celsius would be a suitable temperature according to the model. Finally, we're going to finish with a modelling problem, which is very common. One of those ones that's almost guaranteed to come up in some capacity. This is type of problem where you've got an exponential model, but you can use logarithms to turn it into a linear one to then make it easier to find missing constants. So then you can have a good exponential model. So in this problem, we've got a research team investigating a particular social media user, and they've observed that the number of views, n in thousands, following a viral post after t days can be modelled by the equation. So you've got there that n equals a times t to the power of b, where a and b are constants. So if you plot n against t, you'll see an exponential relationship. Figure 1 shows the linear relationship between log t and log n. So we can see that when we do log n against log t, we get a linear relationship instead. So you can see that all on that figure 1 there. The line meets the vertical log n axis at 2.5, and the straight line passes through the point 511.5. The first thing we're going to do is going to find a complete equation for the model in the form n equals at to the power of b. So there'll be a few different approaches you can take here. What I'm going to do is start off with my exponential equation, n equals at to the power of b, and I'm going to take logarithms of both sides. Normally, I'm just going to use log to base 10 here. You normally don't actually really have to write the base 10 if you just write log. It is implied that we're working with base 10, but just to make it nice and clear, we'll keep our base 10 in there. So I'm literally just writing log to base 10 in front of both sides there. On the right hand side, what I can do is use the laws of logs to separate this out. Now, log xy is log x plus log y. So what I'm going to do is separate the a and the t to the power of b out here. Just be really careful how you separate this, because in that bracket there you've got a times t to the power of b. So it'll be log a plus log t to the power of b. What we can then do is we can use the power law to bring that b to the front, so this becomes b log to base 10 of t. And now what I've done is I've now got this in a linear form. If I plot log n against log t, this produces a straight line. This is because log n and log t are my variables. B is my coefficient of log t, so this b will represent my gradient, and this log to base 10 of a, well, this is just a constant. A is a constant, so log of a constant is still a constant. This will be my intercept. So now I can relate this to the equation of my line. So if I look at the figure here, as I said, b is going to be my gradient. So my gradient, I can just find that from the figure there. If I just do the change in log n over the change in log t, so I'm going to do 11.5 take away 2.5, and I'll do 5 take away 0. I'll get that b is 1.8. So b is 1.8, and then log a is my intercept. So if I, again, look at the figure there, I know it intercepts there at 0, 2.5. So log to base 10 of a represents the intercept, which is 2.5. And this time, though, I'm going to have to do a little bit more work, because this is that I've got here that log a is 2.5. So if I do 10 to the power of 2.5, this gives me I'm told to leave this to 3 significant figures. So if I do 10 to the power of 2.5, I get 316 to 3 significant figures. This wouldn't quite be it, however, because I'm asked to find the complete equation for the model. So just finding a and b is not enough here. What we're going to need to do is we're going to need to put a and b back in as so. So we get there, that's going to be, should we just make it nice and clear? We'll write it like this. We'll get n equals 316 times t to the power of 1.8. And that's my complete equation for the model. Now I can, if I know the number of days, I can just sub in any value t to find n here. So next we're going to look at part B. And I'd say these are probably the questions on these ones that I know my students usually struggle with the most. These with reference to the models interpreting the values. So with reference to the model, interpret the value of the constant a. Okay, so basically, what does that 316 mean? Okay, it's got to be within context of the question. So my tip with these types of questions is we need to look at, well, when does this 316 come up? I think a lot of time people just go, oh, it's the initial value, but that's not the case here. Okay, when t is 0, n will be 0 here. So that's not what that 360 is representing. What I need to think about is, for what value of t do we get n equaling 316? Now, when t equals 1, that will just mean you do 1 to the power of 1.8, you times it by 316, you'll get n as 316. So we know that when t is 1, n is going to equal that 316, or n is going to equal a. So we've interpreted the maths of that, okay? So when t equals 1, and that's when you're going to get that constant value of a. Now we just need to interpret this as it should be. So when t equals 1, well, that's just 1 day. So what this means is, after 1 day, the post had n number of views. Okay, remember n is the number of views. The post had 316,000, because again, just be careful there. N is in thousands here. So after 1 day, the post had 316,000 views. And finally, this part C, another type of question I like to do. They like to kind of test your model with a value to see if it's valid or not. So we're told another social media user finds that after 36 hours of posting, their post had 2 million views. Comment on whether or not the model would be suitable for this user. So we're going to see if this other user would find this model helpful. So what we're going to do is test out to see if our model gives a similar value to what they get in reality. Now, they find that after 36 hours of posting, they get 2 million views. Now, yet again, we've just got to be careful of our units here. T is in days here. So we're going to look at T. Now, 36 hours, that's going to be 1.5 days. So T is going to be 1.5. So what we need to do is sub in T equals 1.5 into our model. This time we can use the 316. Don't worry too much about using the exact value that you got here, because it's just a model. So we just want to see, is it roughly in the right kind of, is it roughly a kind of good figure that's near to that 2 million. So if we put that in our calculator, we put in n equals 316 times the 1.5 to the power of 1.8, we get that n is 655.62. Now remember, n is in thousands here. So we're going to, so that's not actually going to be 655 views. That's going to be approximately 656,000 views. Okay. So we need to mention that in our answer. So we can say the model predicts approximately 656,000 views. Okay, we'll just round here because it's just a model. Let's just use it as a prediction. So it predicts approximately 656,000 views. This is significantly smaller than 2 million. Okay, in the questions, you'll need to compare the two numbers. They'll want to see you mention the number that you've calculated and the number that has been found in reality. Don't just say like, oh, it's not a good model because of that. You've got to have a justified reasoning. Okay, don't just say, oh, as t gets really big, it's not valid, or you're just looking to compare the two values here. And it's important here that I'm saying significantly smaller, because let's say your model predicts like 1,968,000 views. Okay, now it's not bang on 2 million, but it's just a model. It's not going to be perfect. So if you got a number like that, that would be fine. Okay, there's not like a actual rule as to where you do and don't accept it, but certainly just using kind of your logic here, 656,000 is a lot less. Okay, we're talking about a third really of the 2 million. So that is significantly less. So that's why we can say that the model wouldn't be suitable. So then we just need that conclusion. So compare the numbers and then just make sure that you do state whether the model is suitable or not. Okay, and that will do it there for logarithms and exponentials. The next video I'm going to be producing is going to be on probability. And I know probability is paper 3, but please don't leave paper 3 content to just after you finish paper 2. 7 days isn't going to be enough to go through everything there. And I know a lot of people do struggle with probability. So I've come up with some really good questions for that. In the description below, that will be there, so you can start working on that. And in the next few days, I'll put the video going through the solutions of that. So if there's any questions you still got about this video, or any topics in particular you'd like to kind of go through ahead of your exams, let me know in the comments and I'll see what I can do there. But that'll be it for this video. Thank you for watching, and I'll see you in the next one.